Let's be real. Have you ever actually stopped to think about what happens after you swallow a pill? It's not just some simple trip down to your stomach. No, it's this incredible secret journey with its own rules, its own gatekeepers, and a very specific mission. Today we're going to follow that journey step by step.
It kind of feels like magic, right? How in the world does a headache pill know to go to your head? Well, the truth isn't magic, but it is a really fascinating science. And by the end of this, you're going to see the beautiful, elegant system behind it all.
All right, so every grand tour needs a map and a guide. Before our drug can even set off, we got to get our terms straight. First things first, what is a drug anyway?
This entire adventure, the whole thing, it's all mapped out by a field called pharmacology. You can think of it as the science that decodes the secret conversation that's always happening between a chemical and your body.
So what is a drug? At its very core, it's just a single chemical, a substance with a known structure. It's the active ingredient, the star of our show. You could even call it a molecule with a mission. And that then brings us to the word medicine. A medicine is the final product, the thing you actually use. It has the drug in it for sure, but it also has other ingredients. They're called excipients, and these are the things that help stabilize it, deliver it, or even just make it taste better.
So here's the crucial difference. You ready? Think of the drug as the star singer. The medicine is the entire concert. It's the singer, the stage, the lights, the whole shebang, all of it working together to deliver that final performance.
Okay, so once that medicine is in your body, it does not get a free pass. Your body has this really strict set of rules for any chemical that comes in. This whole process is called pharmacokinetics, which is just a fancy way of saying what the body does to the drug.
The easiest way to think about pharmacokinetics is to picture the body's security guard. This guard decides what gets in, where it's allowed to go, and exactly when it has to leave. And this guard follows a really strict four-step process for every single drug, which, conveniently, we can remember with the acronym ADME.
Yep, that's ADME. Absorption, distribution, metabolism, and excretion. This is the literal path our drug takes through your body. So let's take a look at each stop on this tour.
First up is absorption. This is the main security checkpoint. The drug has to get from wherever you took it, let's say your stomach, and successfully get into your bloodstream. By the way, this is exactly why some pills need to be taken with food and others on an empty stomach. It all affects how well they can pass this first checkpoint.
Next stop, distribution. Once it's in the bloodstream, the drug gets swept along and pretty much travels everywhere. But some places are like VIP lounges with extra security. The brain, for example, is protected by something called the blood-brain barrier, which is basically a tightly packed wall of cells that stops most chemicals from just wandering in.
Then comes metabolism. You can think of this as the drug's mandatory costume change. This transformation happens mostly in the liver, where this whole team of enzymes, especially this famous group called cytochrome P450, chemically alters the drug, usually making it inactive and a lot easier to get rid of.
And finally, we have excretion. The show is over. The drug and all its metabolized byproducts are squirted right out of the body. Your kidneys are the main bouncers here, filtering everything out into your urine to be flushed away for good.
So that's the tough journey the drug has to survive just to get to its destination. But once it arrives, what about its mission? Well, that's the other half of the story, pharmacodynamics, or what the drug does to the body.
So if pharmacokinetics was the security guard controlling the journey, pharmacodynamics is the mission itself. And the best analogy here, by far, is a lock and a key. The drug is a precisely shaped key, and it's designed to find and fit a very specific molecular lock somewhere in your body.
And these keys can work in two totally different ways. An agonist is a key that not only fits the lock, but actually turns it, firing up a response. But an antagonist? That's like a key that fits perfectly, but then breaks off in the lock, jamming it up and blocking any other key from getting in.
Now, for this whole lock and key system to work, two things are absolutely critical. The first one is affinity, which is really just how well the key fits the lock. A drug with high affinity binds super tightly, like a perfect match.
But just fitting isn't the whole story, right? The second thing that matters is efficacy. That's the ability of the key to actually turn the lock once it's in there. This is what separates our two types of drugs. An agonist has both affinity and efficacy. It fits and it turns. An antagonist has affinity, it fits perfectly, but it has zero efficacy. It can't turn the lock at all.
So what are these locks that the drugs are looking for? They're not just random. Drugs are designed with incredible specificity to target one of 4 main types of proteins in our bodies: receptors that act like little satellite dishes for signals, ion channels that are like gateways, enzymes that speed up reactions, and transporters that act like cellular taxis.
So we've followed the drug's journey, we've seen its mission. But why does all this complex science matter to you? Well, because understanding these principles is exactly how we use medicine safely and effectively out in the real world. This basic science has just blossomed into these incredible new fields. For instance, pharmacogenomics looks at your unique DNA to predict how you'll respond to a drug, and pharmacoeconomics even helps us decide if a new, super expensive treatment is actually worth the cost to society. It is all connected.
And this science has real life-saving applications today. A simple genetic test, which comes from pharmacogenomics, can tell a doctor if a common drug might be dangerously toxic just for you. And molecular pharmacology, that's how scientists design what they call magic bullets, like antibody drugs that can literally hunt down and target cancer cells with incredible precision, all while leaving healthy cells alone.
Here's one last fascinating piece of the puzzle for you. Ever wonder why you have to take a medicine for a few days before you really feel its full effect? It's because it takes about 3 to 5 of the drug's half-lives, that's the time it takes for half of it to leave your body, to build up to a steady, effective level. It is all calculated.
So from the body's security guard managing the journey to the molecular lock and key defining the mission, every single medicine tells a story. The next time you see a simple pill, think about that story. What lock is it designed to find? And what incredible journey will it take to complete its mission?